Power and efficiency. What we're going to be looking at today is how we calculate power, how we calculate efficiency, and some of the nuances between different types of circuits. More of a review than anything else. So let's get started. Power and efficiency. Well, we should have a general understanding that these three equations are going to be used. P is equal to E times I. P is equal to I squared times the ohms, and P is equal to E squared over the ohms of a circuit. All three of these are used to calculate power in an electrical circuit, and it really doesn't matter what type of circuit it is. It could be AC circuit, DC circuit, three-phase circuit, does not matter. These three equations are still true. This is called true power, and true power is something that will become significant over level 2 training, is measured in watts. And the way that we represent that with a measurement would be with a W. So 10 watts or 10 Ws. True power you can always consider as the power that is accomplishing work. And for most people, the easiest way to sort of correlate that is to say, okay, how much heat is it actually giving off? Heat or motion or light, as opposed to other forms of power, which we'll take a look at later on in your training. Let's get back to these three different equations then. We've got three different ways of calculating power. So if we had a resistor that had 5 ohms worth of resistance and it had 2 amps worth of current flowing through it, then we could utilize our I squared R calculation to work out the watts, which would be 20 watts. If we had a resistor that had 15 volts across it, and the 15 volts across, it also had 5 ohms of resistance, then we could use E squared over R and get 45 watts worth of power that's consumed by the resistor. So remember, it's the amount of heat when we're talking about a resistor that is given off as the voltage is applied across it and current flows through it. The last one, let's say we had 25 volts and 3 amps flowing through. Well, then we can use the top one, E times I, and that would give us a watt rating of 75 watts, or a watt consumption, I should say. It would be consuming that much power. All right, so let's take a look at this within a circuit. It's important to realize that in any circuit, any circuit, and when I say any, I really mean any. So a DC circuit, an AC circuit, a single phase circuit, a three-phase circuit, a series, a parallel, a 3-wire, a combination circuit, any circuit, this equation will be true. P total is equal to the power consumed by the first object in the circuit plus the power consumed by the second object plus the power consumed by the third object, so on and so forth. So it's important to realize that because it then opens up some available means of calculating values that you may not have considered previous. So let's just very quickly look at a series circuit and a parallel circuit. 1, 2, 3, 4 resistors. They are going to be 5 ohms each. And we're going to have a source voltage of 120 volts. So let's say these are tiny little heaters. So I have 4 heaters. perhaps they're baseboard heaters, but 5 ohms would be an extremely low amount of resistance. Anyhow, 120 volts, I want to know what the power consumed by one of the heaters is and what the power consumed of the total circuit is. So if we want to work out the power of one of these, we need to first know what the current flowing through the circuit is. Another way of achieving our end result would be to simply work out what the voltage is across each, because remember, it doesn't matter what equation I use. I can use this one, I can use this one, and I can use this one. It's up to you, right? So I'm going to choose to work out the current value, and then I'm going to use this equation to work out the power consumed by just one resistor. So I can take my calculator here. You can't really see a whole lot from the glare, but that doesn't matter. You have a calculator, which I trust you can work on your own. 5 ohms, 120 volts. So let's see, if I want to get the total current, I need to know the total resistance. So that means adding them all together. 5 times 4 equals 20 ohms. I have 20 ohms worth of resistance total of this entire circuit. And we know that Ohm's law, I is equal to E over R, means that I should be able to calculate what the current is. So if I take 120 and divide it by 20, I get a current value of 6 amps. 6 amps, there we go. So let's put a fun little arrow on there. 6 amps. All right, now I have the current and I have the resistance. I'm going to do I squared R. I squared R is going to give me my power for one. So 6 squared times 5 equals 180 watts. Each one of my resistors is identical in value, which means that it should be 180, 180, 180, 180. So if I multiply my 180 times 4, we should get P total. Another means of doing this would be to simply take 120 times 6. There's really 2 different ways. There's actually 3, but we'll just leave it at 2. So you can either take 120 times 6 or 180 times 4. It's up to you. So I'm going to do, well, I'm not even going to tell you which one I did because it doesn't matter. 720 watts would be the total power. All right, so if that is total power for a series circuit, let's take the exact same heaters, and now we're just going to crank them into a different arrangement. It's same heaters, but now we're going to put them in parallel with that same source. Source hasn't changed, still 120 volts. It's still 4 heaters. And we still have 5 ohms of resistance each. And we're going to work out the same thing, P1 of one resistor or heater, how many watts, and P total, what's total power consumed. So is the power going to remain the same? Of course not. Come on. That doesn't make any sense. Can't be the same. How would it be the same? The power is going to change from this circuit to this circuit. This is the only thing that doesn't change. The ohms of resistance, that's a physical property. The current that flows through, the voltage across, those are going to fluctuate depending on what type of circuit you put them in. So at this point, how many amps would I actually have flowing through each one of my resistors? Well, we can use Ohm's law, and Ohm's law is E over R, 120 divided by 5. 120 divided by 5 gives me 24 amps. 24 amps means the power that I'm going to have consumed by one resistor, let's go up here, I squared times R. So that would be 24 squared times 5. 2880. What about the total power then consumed by the entire circuit? The total power is going to be equivalent to the 2880 times 1, 2, 3, 4. Or what we could do is 120 times total current. What would the total current be here? Well, total current should be the sum of all of these currents. So that would be 24 times 4, 96 amps would be the total current. So it's up to you, 120 times 96 or 24 times 4. They'll both render the same answer. So I'm going to do, well, again, I'm not even going to tell you because it doesn't matter. but we get the same answer, 11,520 watts. So P1 plus P2 plus P3, right, renders the same answer no matter what process we happen to use. All right, let's take a look at power in regards of a full circuit. So this has to do with line drop and loss. Line drop and loss. Let's look at a basic circuit like this. There's a wee little resistor in there, and it's a 2-wire circuit. And we're going to do a little load at the end here. And we're going to do this. I'm going to draw a dotted line. Well, that one didn't work out so well as dotted line. Okay, I'm just going to do a wavy line. There we go. It works out much better. Just to give us a little bit of separation on the circuit. In the middle, we are going to have my loss. On this side, power output, and this side, power input, because my source is over here. So let's first discuss line drop. I'm going to put a little chunk of resistance in here, 0.1 ohms, 0.1 ohms. And we're going to put a load value in of 25 amps. And the voltage of the source is going to be 240 volts. So first thing we want to do is calculate the line drop. So I'm going to calculate the voltage. And the line drop is going to be the portion of voltage that is dropped across the conductors combined that does not reach the load. So we are going to start by putting on some arrows because we all love arrows. 25 amps, 25 amps, 25 and 25. So 25 amps times 0.1 of an ohm gives me 2.5 volts. That would be the voltage measured across this one chunk of resistance. And so what we start with is our 240 volt source, and we subtract the total line drop of our circuit, which is 2.5 and 2.5. And what that equals is the load voltage on the other end, which is 5 volts less than my source voltage. So that would be 235 volts. If we wanted to calculate what the percent line drop is, we would have to take our line drop and divide it by our source voltage. So this would then equal 2.08% line drop. Okay, so this would be my percent line drop. On the other hand, we could work out what the watts lost are and how that represents itself when it comes to line loss, and then we're going to look at efficiency. So let's look at the input power, 25 and 240 volts. This is the input, or P in. P out is over here, and we're going to have losses in the middle. So P in is 240 times 25. So 240 times 25 gives me 6,000 watts. In the middle, we have losses. And so again, we take the input and we subtract the losses from it. So I'm going to take 25 times 2.5. Gives me 62.5 watts. So subtract 62.5 watts from both of my conductors. So I've got 6,000 minus 62.5 minus 62.5 gives me 5875 watts output. Now, how do we calculate the representation of these power values in regards of the efficiency of the circuit? Well, these are the losses. And it's calculated a little bit different than percent line drop, right? Percent line drop, what did we use to calculate this? We took the line drop and we divided it by the source voltage and multiplied by 100. When we do percent efficiency, it's a correlation between the input and the output, not the losses in the input. And so the equation that we use for this is P out divided by P in times 100. And this should give me my percent efficiency. So with this circuit here, 5875 divided by 6,000 times 100 gives me 97.91%. And this would be efficiency. So two different calculations there. Let's take a look at one final application of efficiency and how we can use that with calculating values for motors. All right, so let's look at a motor with this percent efficiency value or percent efficiency calculation. So I'm going to say motors and percent efficiency. We need to know first the efficiency formula. Percent effic is equal to P out over P in times 100. And when we're dealing with motors, the second most important aspect is this: horsepower, or one of these horses, is equal to 746 watts. This is imperial. And so in North America, we use for mechanical output, and this is metric. If you were to go to Europe and install a motor, the output would be measured in watts. So in North America, what we're going to have is motors where the input and the output are both indicated on the nameplate. So here, this would be power input, and that's typically going to be on the nameplate as the volts and the amps, the rating of the motor. Here is going to be the output, and that's going to be rated in horsepower. The losses in the middle are typically going to be given on the motor as a percent efficiency. So if we wanted to do a calculation with a motor, we could determine what the total losses were. So let's do two calculations with motors, and then we'll see what we get from that. So first thing, here is a motor. It has a 20 horsepower output, and the input that we're going to have for this is going to be 80 amps at 240 volts. And what we want to calculate from this is, first, what's the percent efficiency? What is the P input? It's P output. And what are the losses? All of those items. So let's start with one that we can calculate right away. Let's calculate power input, 240 and 80 amps. 240 and 80 amps gives me a total input power of 1920 watts. Or sorry, 19,200 watts. 240 times 80. What about over here? What's the output? That's 20 times 746. Power output, 14,920 watts. What are the losses in between? Well, if we take the output and the input, let's subtract these two values. So 14,920, take that out of 19,200. So 19,200 watts minus 14,920 watts gives me 4,280 watts worth of loss. Finally, the percent efficiency, well, we use our efficiency formula, which is the output divided by the input. So 14,920 divided by 19,200 gives me 77.7% efficiency. Let's look at another motor. This motor here is, let's say, 40 horsepower. And what we are told is that it is, let's say 80% efficient. And the source voltage is 480 volts. So what we want to work out is what's power output, what are the losses, what's power input, and finally, what's the amps? How many amps is it drawing? Well, first thing we need to do is take that 40 horse and multiply it by 746. So 40 times 746 gives me a power output of 29,840 watts. So we took 40 horsepower and we multiplied it by 746. Now, we want to work out the losses inside the motor. We've been told it's 80% efficient. What are we going to do? You have a choice here. You can either take your 29,840 and multiply it by 80%, which would give you a smaller number, or you can take 29,840 and divide it by 80% and get a larger number. Remember, logically, the input has to be larger because you're going to lose watts. So we're going to take this 29,840 watts and we're going to divide it by 80%. So that's going to give me, so 29,840 divided by 80%, but remember, you always got to divide by the decimal, so 0.8, 37,300 watts. And I'll just put in brackets here what we did. That was power output divided by percent, or not percent efficiency, but simply the efficiency in a decimal form, right? So we had efficiency in a decimal form. All right, so once we have these two values here, we can subtract them and get our losses in between, right? Power input minus power output. So we're going to subtract 29,840 from 37,300. And what we're left with is 7,460 watts. That's the amount of losses in heat off that motor. So finally, we have the input, the output, the losses. We want to know the amps. How many amps is this thing drawing? Well, remember, amps is a product of, well, we have E times I, which means we could probably take this equation and work out current. I is equal to P over E, and we know both the power and the voltage because the input power is over here, and the input power is 37,300, and the voltage is 480. So 37,300 divided by 480 gives me 77.7 amps. So I hope this was a good reminder or a review of how some of the calculations work with efficiency and power within an electrical circuit.